All right, welcome back. Good morning. So before we begin, any questions, comments, criticisms? Okay, so I'm going to take 10 minutes just to do a little recap of candidate elimination algorithm, because I received a lot of requests to do that. So what we are going to do is go through an example that we looked in the class, but I'm going to go through it a little slower so that you follow all the steps. And for the gradients, you just need to sort of follow the same procedure with some variations, which you will see when you attempt it. All right, so this is the candidate elimination algorithm. It has a bunch of steps, and it's essentially a program that you can easily write. But let's go through an example. Okay, so I'm going to switch to our document camera and look at an example. All right, so let's say we are again looking at our 5-dimensional data set, which is for tumors. And let's say the first example that we see is this circular large light, what is SH? It is smooth. So smooth and thick. All right. So this is our first training example that we get. Before that, in candidate elimination, you initialize your most general boundary and your most specific boundary like this. So even before you have seen this, right? So initialization goes like this. You say that your S is essentially your most specific hypothesis. It just contains this, and general G0 is your contains only your most specific hypothesis or most general hypothesis, right? So right now so your version space is basically everything, right? All conjunctive concepts. So after you see the first example, what you do is you first look at what is its training label. So in this case, it's a positive example. So if you go back to the algorithm, you will see that the first step that you do is if it is a positive algorithm, if it's a positive example, you first check your most general boundary. Okay, you do a quick sanity check to see if there is anything in this general boundary which is inconsistent with your this training example, because remember, this is a version space. So at any given moment, this version space needs to be consistent with whatever training data you have seen so far. So first, when you look at this, now what does it mean to check for consistency? So remember that these are all conjunctive concepts, right? So it means that this should call this as positive, right? And in this case it will, right? Because this is accept all hypothesis. So this accepts everything as a positive or a malignant example, right? So this is fine. Then you go into the real stuff for positive examples, where you go to the most specific boundary, and then you look at every hypothesis in your most specific boundary. Right now there is only one hypothesis in your most specific boundary, right? Then you check if this is inconsistent with your training data, right? It is, right? Because this one rejects everything. So this one is going to call this as benign, which means rejection, but in reality it is a malignant example. That means you need to generalize this, right? So the next step is you try to find the minimal generalization of this hypothesis which is consistent with your training example. All right, so now remember, this is the reject all, right, which means that it accepts nothing. So the number of examples that it calls positive is 0, right? So if you want to generalize it, the next generalization would be a hypothesis which calls at least one example as malignant, right? So of course there could be many specializations or many generalizations of this. It could be circular, large, light, smooth, thin, and so on, right? But there will only be one hypothesis which will be consistent with this training data point and which will be this training data point itself, right? Because this one, when you take a conjunction, it will agree, it will call it malignant, right? Any questions so far? Yes, go ahead. Right. Yeah, so when this is only if you get a positive training example. So first you do a sanity check for your general boundary to remove anything that is not consistent with this new example. Then you go to your, and that's all. You don't do anything else to the general boundary. Then you go to the specific boundary and look at every hypothesis in that and see if there is anything that is not consistent with your new example. And if you find something, then you generalize it, right? So in this case, this is how you generalize it. The next step you do is then you check if there is something in your general boundary which is more general than this. So something that should follow that more general than requirement. In this case, this is more general than this, right? This one is the most general hypothesis. So it will be more general than any hypothesis that you can think of, right? So that works, right? So now you are done with this training example. Then you, go ahead. Yeah, so good question. So I kind of use these terms very liberally, but so each training data point, I call it an example as well, but yeah, so it's a training data point, but it has two parts. There is a actual data, which are the attributes, and also the label. So yeah, you're right. When I call it example, I'm referring to this part. So it should be consistent with the data part. Yes.
So the last step is to check against the general example.
Right.
And see if it's still more general than the example.
No, the last step is that once you have specialized your specific boundary, you see if there is, in the general boundary, there is something that is more general than this. Okay, and I'll come to that. The reason we do that is because that helps you figure out if your version space right now is consistent with everything that you have seen so far, right? Remember that at every step you need to ensure that your version space is consistent with your training data, all of your training data, okay? So now let's go to the next example. Let's say the next example that we get is this. It's circular, large, light, irregular, thick, and this is also positive, all right? So the first step you do is check if the general boundary agrees with this one, is consistent with this one. In this case it is, because it's a positive example and this is going to call everything positive. So you're good on that. Then you check your specific boundary. Right now there is only one concept in your specific boundary, but so the next thing you check is this consistent with this, all right? So what that means is that this concept is going to call only those examples positive or malignant which have these things in them, right? It should be circular, large, light, smooth, and thick. But if you look at this example, it disagrees on one of them, which means that this specific boundary right now is not consistent with this example, which means that you need to modify it, okay? So again, when you go back to the steps, so the next step is you consider all consistent minimal generalizations of this this hypothesis, right? So the minimal generalization of this would be in which you turn one of them as question mark, right? And the only one that will be consistent with this will be okay, because this one will agree with this one, and the one that is offending will get ignored anyway. So this way what you have done is you have ensured that your most specific boundary is consistent with your training data so far, with this training data point, and your most general boundary is also consistent with your training data point, right? Last step that you do before you move on to the next example is to check if there is a corresponding most general hypothesis for this, and right now there is. The reason we keep doing that is because that helps us ensure that even though we have changed our boundary, nothing that we have seen before this becomes inconsistent, because again I'm reiterating, but version space needs to be consistent with all of your training data, right? But the beauty of the candidate elimination algorithm is that it does not keep all of your training data. Once you see a training data point, you process it, you throw it out, right? So then how do you ensure that when you keep changing your boundaries, your new data point is the new boundary or the new version space is still consistent with what you have seen so earlier, right? Because you have thrown it away. The reason you can do that is because of this step, because you always ensure that whenever you change your training data or whenever you change your boundaries, it needs to have something on that end, and that happens because of the version representation theorem. But that is essentially the basic step. Okay, so far we have looked at training data point 1, training data point 2. Now let's see if we get another data point. And right now, just to make it interesting, we are going to say that it is these are the attributes. So this is thin, this one was thick, and this is a negative example. All right. So when it is a negative example, you have to go in reverse. You have to do something opposite. So you have to first check if there is anything in your most specific boundary which does not agree with this one. All right. What does that mean? Which means that whatever is in your most specific boundary should call this negative. Otherwise, this version space will not be consistent, right? So let us see that. Now, this hypothesis will only accept those data points as malignant or positive which are circular, large, light, and thick, right? Now, this one you can clearly see that this one is oval here, and other things also disagree. So which means that this hypothesis will call it negative, and this is negative. So it is consistent. So you do not change this at all. Then you go to your general boundary. The next thing you do is you see if any hypothesis in your general boundary is inconsistent with this training data point. So what happens here is, of course, this accepts everything as positive, right? This is an accept all. But this is a negative example, which means that this hypothesis is inconsistent with this example, all right? Which means we need to modify it, all right? Any questions so far? Yes?
So you're saying checking against the specific boundary, it would have to be negative. Would that also turn something in the specific boundary to a question mark?
If you find an inconsistent hypothesis in the most specific boundary, you just throw it out. You don't change it. If you look at the steps of the algorithm, right, you don't change it. So let's look at step number 1 in Cx equal to negative, right? So you only remove those hypotheses in which are not consistent, but you do not change, you do not specialize it anymore.
So let's say like the one that you just heard, the S2, let's pretend for a moment, that is a bit consistent, you just remove the S2.
You just remove.
S1.
Right. Well, you don't move back to S1, you just remove it, and at that point there is something wrong. The reason that will not happen is that because your data is being generated by a concept, that situation will not arise unless there are mistakes in the data, that your most specific boundary becomes empty. Because the reason your most specific boundary contains all those hypotheses which are consistent with your training data, right? Which would accept all the positive examples and reject all the negative examples. So if at any case you are left with no hypothesis like that in your S, that means there was a mistake in the data itself. That also is a good feature of candidate elimination algorithm, that it can notify you that there is an error. But that will not happen. I see what you mean. So you just remove it, but do not worry about it becoming empty, because that will not happen if your data is not, if there is no errors in your data. Okay? All right, but you do not change it. Okay, so going back. So now what we do is we have figured out that this one, this hypothesis is okay with this one, right? But this one is not. So now we have to generalize it. Okay, so now we consider all minimal specializations of the general boundary. Okay, so right now general boundary had only one concept, and the minimal generalizations of this could be many. So it could be circular, question mark, question mark, question mark, question mark, and you can list many, right? You can replace this with circular or oval, you can replace only this one with smooth or large, and so on, right? But you need to only enumerate the ones that are consistent with this example, right? So for example, I could write this one will call this as negative, so this is fine, right? But you do not need to write the oval one, because the oval one is going to call this positive, right? The oval hypothesis will call everything, all of those examples as positive which are oval, but this one in reality is negative, right? So you will not consider this. So just to avoid writing too many hypotheses, that's a general easy rule, is you just consider these and flip them and enumerate those. So if it is oval, then consider this one. If this is small, then consider question mark large, oops, sorry, question mark, then question mark dark, question mark. The reason I'm only flipping one is because that's the most general hypothesis, that's the minimal specialization that you can make. And there's one more point that I want to make here. Question. What's that?
You can't say dark because the first one.
Yeah, but we'll come to that, because right now you don't know. Right now all you can see is this training example. That's a good point, and we'll come to that. But right now all you are saying is, I want to consider all those specializations of this which are consistent with this example. Okay, and then there's a next step. Question mark, irregular and question mark, and question mark, and thick. Okay, these are the all minimal specializations that are consistent with this example, because that's the rule, that's the step. Okay, it could so happen that none of that you are not able to find any here which are consistent with this example. In this one it's not happening, but in general it could happen. You don't stop then. What you do is then you consider the next generalization, which means that you might consider next specialization, which means you might consider turning two of them as actual values, and so on. So don't stop if nothing comes up with only one question mark. Okay, but anyway, in this case doesn't happen. So these are all the minimal specializations which are consistent with this example. But there's one more step, which is now you try to find in the most specific boundary something that is more general than this. Okay, and that comes to your point. So for example, this one, there is a more general than hypothesis here, right? Because this one has CI and all question mark. This has CI and something. Sorry, more specific than. So this one is okay. This one is okay because there is a large and there is a large one here. This one, well, let me just go the one there. Okay, this one is okay, right? This is thick. But now let's look at this one. Dark, but there is no hypothesis here which is more specific than this one, but contains dark, right? Which means that this is not going to be considered anymore in the general boundary. Same thing with this one. Right? This one is also not going to be considered because there is no, this one is fine, right? More specific, I'm sorry, right. So there is nothing more specific than this here which contains IR. So you remove that. Now why are you doing that? Of course, this is what the algorithm says. But the reason you are doing this is because by this step, you are ensuring that whatever changes you are making to your version space is still consistent with your training data that you saw earlier. Okay, so that is the beauty of this algorithm, is that it doesn't have to maintain the training data in memory, but every time, because of this relationship, it ensures that you are still being consistent with your existing training data.
This is my next training data. I get a dark, which is possible, but then remove it from this.
So the question is that if next time you get a dark which is positive, right? You get an example in which it is dark but it is positive, right? But it's fine because dark, looking at this data so far, you know that dark is not a useful attribute because it is dark for both positive and negative. Is that right? Oh no, it's because dark is not, that attribute is not cannot differentiate between positive and negative. So it automatically ignores that. So that's actually a good point. All right, so this becomes your G1 at this point because you have removed the ones that are not specific, that do not have a specific thing at the top. All right, so let's consider one last example. This one is oval, large, light, irregular, and thick. And this is positive. Okay, so positive means that the first thing you do is you check if there is any hypothesis here which is not consistent with this. So let us check that. This one is not, right, because this one calls anything which is circular as malignant, but this one is oval and malignant, right? So you remove this. Sorry, I should. Well, it's fine. Right? So now you are creating a G2. So G2 will not contain this. This one is fine because this one has large, this is large. This one is also fine, thick and thick, right? So now your G2 will only have these two. So just reiterating the point that I made to your question earlier over there is that I'm only going to remove these but not going to modify it anymore, because in the steps we do not modify the G boundary when you get a positive example. You just clean it up a little bit, all right? Now, but we have to modify our S3. So the first thing we see is this hypothesis consistent with this one, right? So is it? It is not, right? Because it's going to call anything with, this one calls anything with circular and other things as positive, but this one has oval, right? Which means that we need to generalize this one. So we have to consider the generalizations of this one, and the generalization of this one which is consistent would be question mark, large, light, question mark, thick, right? This one is fine because this is consistent with this. The only thing we need to check now is that is there a more general hypothesis here which covers it, and in this case it is. In fact, both of these are more general than this hypothesis, right? So this is fine. So if we stop here, then this is our version space. Okay, any hypothesis that is between these is part of your version space. So this is how you learn using your candidate elimination. So if you follow the steps of the algorithm closely, then you will get to this, but you also need to understand why are these steps there. The steps are there so that you are always maintaining this property that the version space is consistent with your training data. And the second step, and another thing that we do is we always ensure that this is the most specific boundary and this is the most general boundary. All right? Any questions? Go ahead. Everything. It could happen, right? So the question is, can it happen that the most specific boundary has more than one elements in it? So in this case, you can see it won't happen because you're going one by one, but there could be scenarios, especially your attributes are not binary. If they can take 3 values, you can have more than that. And another thing I want to point out don't get confused, but candidate elimination can also be applied when your concepts are not conjunctive. You can actually apply it to anything, except that the way you figure out what is more general, more specific will be different. All right? There's another question in the back. Yes, go ahead. Yeah. Right. Yes. Yes. So actually, that's the same question that he had asked as well. The answer is that for this kind of example, it won't happen. But if you have other cases, like if your attributes can take more than 2 values, then you will see that it could happen. So there could be scenarios where, there is no guarantee that it will only have one hypothesis, but in these simple settings, it won't. So I guess that's what is sort of driving this. But yeah, in general it could. Any other questions before I stop with this? All right, fantastic. So let's move on to our next topic. So far what we have done is just a recap of last week, a recap of earlier class. But now we are going to move to what I actually wanted to teach today, is our disjunctive concepts, right? All right. So we were looking at monotone disjunctions. That's another kind of a concept class, like conjunctive concepts. So monotone disjunctions are actually easier to understand, which essentially means that you call anything as positive or malignant if it has one property or another property or another property, right? So it's either small or thick or something, right? So that's the idea of disjunction. And monotone disjunction is in which you only consider the positive value of the attribute. So let me set our notations for that. So K monotone disjunctions. So first of all, let us make sure that we understand our data. Okay, so we are still dealing with binary data, which means that your data x, data point x is a small x, is a data point or instance or example. This is a mathematical way of saying that it has d binary attributes, right? 0, 1 raised to power. It's a set. It can take either 0 or 1, and there are d such values. Okay. Earlier we had used some other values as well. So we could say it is false or true or -1 or 1. But let us be consistent from now on. We are going to consider x as a vector of d elements. Each element is either 0 or 1, right? So like d elements, vector, and it's 0, 0, 1, 0, 0, 1, 0, something like that, right? And the target, the label is true. Label is fine, it's one or the other, right? When I write a vector, if I enumerate it, I'm going to write it like this: x1, x2, x3, x4, x5, x6. Let's say I have 6 attributes, and I'm going to put a bar if it is 0 and no bar if it is 1. This is just for denoting it. All right, so that's, whenever you see this, it means that x1, the first attribute, takes the value 0. And if, sorry, go ahead. What is the word after K? Oh, monotone. Sorry. Yeah. Monotone. And I'll explain why it is monotone. So this is how we will denote it. But in when we put it on a coordinate space, we are going to use zeros and ones to denote it. All right. The next thing I wanted to tell you is right. So what is a monotone disjunction? Monotone disjunction means that the concept is going to be of this form: x1 or x3, which means that I'm going to call only those objects or those elements as positive or malignant which are 1 for x1 or 1 for x3. Okay, so this is a monotone. This one is not a monotone. So this is right, this is not right. Not a monotone. All right. Why are we doing this? Just to make our life easier, right? Which also means that K monotone disjunctions might not be very expressive. That, for example, maybe your real objects do need to be expressed like this, but in this definition you can't. In this definition, you are forced to consider only these kind of expressions as your target concept. Go ahead.
Why is that? Why can't we compare X bars versus regular?
It's a good question. So the reason being that for analyzing it, it's easier this way. There's no reason from the application to do this. In reality, we shouldn't be doing it. And in fact, in reality, when we look at actual algorithms, they would not be making assumptions like these. But to do our analysis, we are kind of making this assumption. We are saying that our essentially, if we go back to our notion of concept classes, so this was our big concept class. This one was our small conjunctive concept class. We are again drawing another boundary. It could be overlapping, I don't know. But this, so you're making your concept class small, your hypothesis class small, so that you can search easily, right? But there is no reason to do it from the learning perspective. In fact, you make your concepts less expressive. But anyway, so that's the rule, all right? So the next thing we want to do is we want to come up with an algorithm which can learn these k-monotone disjunctions, right? Try to find this from the data. Right? So to do that, the first thing we said last time was we are going to put these data points in a coordinate space. Okay, so we're going to geometry now. So think of, let's say you only have two attributes. Let's say D is equal to 2, which means that your data points are two-dimensional vectors. And there could be 4 data points like this. There could be x1, x2, x1, x2 bar, x1 bar, x2, and x1 bar, x2 bar. What this means is that this data point is basically 1 and 1. This is 1 and 0. This is 0 and 1. And this is 0 and 0, right? If it is 3-dimensional, then you can have 2 power 3, 8. Go ahead. Yeah, that's because I drew more, right? You're right. But so here we are considering D equal to 2, so it will have 4 values, which means that I can put it in a 2-dimensional space. So let's say this is x1 and this is x2. So this point will be right here. This point, x1 is 1 and x2 is 0. This will be right here. This is x1 bar, x2 bar, and this one is x1 bar, x2. Right? So you can put your data in this 2-dimensional space. If your data is 3-dimensional, then you have to put it in 3-dimensional space, and so on. So just to make it easy to draw, I'm going to just deal with 2-dimensional data right now. Okay? So the first thing that I said last time was that if your data is being labeled by a k-monotone disjunction, it means that you can draw a straight line to partition the two types of points. So let me just explain it a little more. So what does a concept do, right? Going back to our second class, a concept essentially partitions your data into 2 parts. Some it calls positive and some it calls negative, right? Of course, a disjunctive concept will also do the same, right? Which means that whenever you label your data points with a concept C, some of these will become 1, some of them will become 0, or positive or negative, right? So for example, one conjunctive concept could be this, x1 or x2. This is a monotone disjunction, right? So let us first see which points out of these 4 will it call as positive. Any ideas? Which points will which examples out of these 4 will this concept label as positive? Right. So except for this one, all of these will be labeled as positive by this concept, right? This will be positive, this will be positive, this will be positive. I want to so let's go. So this is positive, and this is positive. All right? And this one is negative. Now you can draw a straight line which differentiates between these two. Yes, go ahead. No. So in the monotone, so this is the disjunction, x1 or x2. Now in this one you are only considering the positive values when you are calling something malignant. But when you apply it to the data points, now the data points can take positive or negative values because they are all the data points. Some of them will be labeled as positive by this. That's just a Boolean expression. Some of them will not be. So that's the point. But you cannot write x1 bar or x2 here. You cannot have that. That is not a monotone disjunction, essentially, right? So that's the point. Yes.
But when you were explaining that x1 bar or x2 is not monotone, if you look at this 0 or 1, the second example, x1 bar or x2, it should not be monotone because it's saying you said 1 or 1 should be a monotone and 0 or 1 should not be a monotone.
Right. So there's a little confusion here. I think so. The monotone property needs to be of a concept. The data points will be the data points. There will be all the data points that you have. Now remember, there could be a lot of concepts, right? So you could have concepts like, so if you go to this concept space, you can have many concepts. A concept which is like this, x1, which calls everything in which x1 is 1 as a malignant tumor. You could have a concept x1 bar. It calls anything that is not for which x1 is x1 is 0 as malignant. You could have a concept like x1 bar or x2. You could have a concept called x1 and x2 bar or x1 bar and x2 and so on. Sorry, right? So you can have many concepts like this. You can have in principle you can have 2 power 4 concepts, right? 2 power d, if you remember, for this 2-dimensional data set. So you can have this all these concepts, but only some of them will be k monotone disjunctions. The ones that will be k monotone disjunction are the ones in which you have only the positive values being considered. All right, but the data points are all of these are the data points. They are all valid data points, but there are only few valid monotone disjunctions. So you could have another disjunction x1 and x2 or x1 bar and x2. So you could have anything, right? Only some of them will partition this. So each concept will partition this data into 2 parts, right? Some of them will be positive, some of them will be negative. What I'm saying is that out of these, the ones that are monotone disjunctions will be separable by a line. Yes, go ahead. I'll come to that line. So the line essentially is the reason I'm drawing a line is because now we are denoting our data point or representing our data points on a 2-dimensional space, right? So when I denote it in 2-dimensional space, I can draw many lines essentially, right? The point being that if these data points are being labeled by a monotone disjunction, then I can always draw a geometric line, and I'll tell you what I mean by draw a line. But I can find an equation of a line essentially such that of course every line divides a space into 2 parts, right? We call them half spaces. So we can always draw a line such that everything that is positive will be on one side and everything that is negative will be on other side. So let me give a counter example and that will help you understand it. So for example, let's say I consider this concept. It is not a disjunction. It's not a monotone disjunction. It is what we call in logic an XOR function, right? So it's either x1 and x2 bar or x1 bar and x2. Right, so let's consider this concept. This is also a valid concept. It is not a monotone disjunction, but it is a concept, right? Now, what does this do? It calls, did I write it correctly? I mean, we also write it like this, right? XOR, XOR, which means it only calls something positive if only one of them is positive. So it will call this as positive and this as positive, and it will call these two as negative. I might have written it incorrectly, but that's the effect I want to have, right? Which means that these ones are positive, these ones negative. Which means that you can never draw a line, right? You cannot find equation of a line such that it puts positive on one side and negative on one side. Is that clear? Right? But all the monotone disjunctions have this property. Yes, go ahead. Yeah, that could happen. For example, if you have an empty, so even a empty, like accept all is a valid monotone disjunction. Now this will call everything as positive. In that case, your job is actually easy. You can draw any line on this side and it will call everything. But the idea being that you can draw a line which puts it in two parts, okay? So the point I want to make here is that if I label my data using a monotone disjunction, then there exists a line, a two-dimensional line, which partitions the positive and negative data points, right? So when I label my data points, I am kind of creating two partitions, and if they are being created by a monotone disjunction, then they will be separable. So go ahead. Yes, I'll come to that. So the next question is, why can I say that? Like, how can I give such an argument? And you can actually prove it. Go ahead. Is the question there? No. Sorry. Well, these are all possible concepts. So any concept. These are not all monotone disjunction. Only this one is monotone. This one is monotone. Actually, in this set, only these two are monotone. This I was just trying to give an example that you can have many concepts. Only some of them will be monotone disjunction, and those monotone disjunctions will be linearly separable. So that's the sequence of arguments I want to make. So let me go to this slide. Right, so I've written it mathematically, but the way you want to understand this is a concept C is linearly separable if there exists a W belonging to R of D. Okay, so these are some notations that will come more and more from now on. So whenever I say W belongs to R of D, it means whenever you see this fancy R, I'm talking about real number space. Okay, so a number line ranging from minus infinity to plus infinity. When I say R power D, that means this W is a vector with D elements, and each element can take a value from minus infinity to plus infinity, right? So what I'm saying is that there exists a vector W of D elements and theta belonging to R, which means theta is a scalar value, one value, but it can go from minus infinity to plus infinity, such that if Cx equal to 1, which means if C of x, that concept, if the concept calls a data point as 1, then the dot product between x and W will be greater than equal to theta. So let me go to my notes before you get even more confused. So let's do basic geometry first, and then we'll come to that definition. So remember, so what is a line, right? So if I have two-dimensional space, if I draw a line, what do I mean by drawing a line? That kind of comes to your point, earlier point. You can represent a line using two values, right? Three values. So this is the equation of a line, right? What does that mean? That if I take any point that is on the line, so if I take this point, let's call it x1 and x2, and if I multiply x1 with w1 plus x2 with w2, then the answer that I get will be theta, because that's the equation of the line, right? I might be going a little too basic, but I just want to make sure that you understand this, because these form the core of linear classifiers and linear models. So from now I will use this more and more. So essentially for a point to be on line, this equation needs to be satisfied, right? So mathematically we also write it as, because you can think of this w1 and w2 as a vector, right? So w1 and w2 This is a two-dimensional vector. And x, this point can also be treated as a vector, right? So if I take a dot product means you multiply corresponding elements and add it up. Then it can mathematically be also written as this. So if this is W vector and this is X vector, then W transpose X is same as W1 X1 plus W2 X2. This is just a notation. So this is also called inner product or a dot product. I'm assuming you're all familiar with this, but just to make sure that we have covered all the bases. So this is so you can think of this the equation of the line. You can also express it as this. Right? Any questions about that? All right. So whenever I write this, it means W. The reason I'm doing W transpose X is because, which essentially means that transpose is that you are making the rows as columns, right? So W transpose can be written as a vector like this, and then you take X is X1 X2, and then you do matrix multiplication. Multiply this with this. So that is W1 X1 plus W2 X2. So that is W transpose X. All right. So if a point lies on this line, then this will be true, right? But if a point is here, let's say there's a point x1 prime, x2 prime, what will be W transpose X for this one, X prime? I'm sorry? I'm saying, what can you tell me about the value of this inner product? We know that if X was on the line, then W transpose X would have been theta, right? Because it is on the line. But if a point is over the line, on this side of the line, then W transpose X prime will be greater than theta. Because on this side, and if there's a point x1 double prime, x2 double prime, then W transpose X double prime will be less than theta. All right. So this equation lets us quickly judge where does this point lie with respect to theta. All right. That is basic geometry. Now coming back to our monotone disjunction. Now since we know that a monotone disjunction means that the points will be labeled in a way that we can draw a line, then if we write an algorithm which can find the equation of that line, then essentially it means that we have found the monotone disjunction. Okay? Because then what we can do is, if we have an algorithm, let's think of that algorithm as a magic box. If that algorithm can give us this W and theta, then you take a new data point, you just apply W transpose X to that. If it is greater than theta, you say it is a malignant tumor. If it is less than theta, you call it a benign tumor, right? So you have learned your disjunction in that case. Right? So that magic box is what we will look at, which we wanted to look today, but probably on Monday, is called the Winnow algorithm. So the idea behind Winnow algorithm is that it tries to learn that equation. Instead of learning the concept, which we were trying to do in candidate elimination and so on, here we are going a slightly different route. What we are saying is that because we know this property of monotone disjunction, that they are linearly separable, then instead of learning the concept, I'm going to learn a line that can differentiate between the two. Now quickly coming to your point, like why do we say that if it's a disjunctive concept there will be line? A simple proof is that if you have a disjunctive concept, right? So what is a disjunctive concept? It is basically a subset of all your D attributes, right? So it could be x1 or x2 or x4. If you write this line, the line over here, which is so this equation of the line will be that line. So let me just quickly use the buffer time a little bit. So if x1 or x3 or x4 is a is the concept, is the disjunctive concept. Let's say this is a 6-dimensional space. That means that the data points are in 6-dimensional. Then if you write an equation of a line in which W is like this, 1, 0, 1, 1, 0, 0, then this will be the line that will that will partition it. Essentially, which means that if you take any data point, new data point, and you do W transpose X, then you can easily see. See, if it is a positive example, at least one of these will be 1 in that, right? Because it's a positive example. So when you do W transpose X, it will have a positive value, which means that a line whose equation is this, will actually differentiate the two types of points. We'll come to this in next class a little more. But when you go back, think along those lines. So we want to learn the k-monotone disjunctions, but instead of exactly learning those, we are going to learn a line because of this relationship between k-monotone disjunctions and this line that partitions the two spaces. All right? All right. Have a nice weekend, and I'll see you on Monday.